Watch how humans seamlessly coordinate multiple senses to accomplish even simple tasks. First, vision guides the search. The eyes scan the environment, processing shapes, colors, and spatial relationships to locate the target bag. Once the bag is located, touch becomes the primary guide. Fingers explore the bag's contents, distinguishing textures, shapes, and sizes to identify the pen among other objects. Human intelligence lies not just in having these senses, but in knowing when and how to use each one. Our goal is to build robots with the same capability, flexibly utilizing different modalities to perform challenging tasks. We achieve this by building modality-specific policies and combining their decisions with consensus weights that vary based on the situation. This adaptive approach enables the intelligent sensory transitions. Watch the policy's adaptive behavior. Vision-heavy processing guides the initial approach to the bag. Once the gripper enters the bag, our learned router automatically increases tactile weighting, using tactile to verify what vision can no longer see. Our policy shows remarkable stability under human perturbation. The robot's continuous tactile feedback allows it to adapt in real time, reattempting the task despite external disturbances. Now let's test our policy's resilience to sensor failure. What happens when one of the RGB cameras is blocked? Our policy seamlessly compensates for the lost visual information, relying more heavily on the remaining camera and tactile feedback to complete the marker retrieval. Our policy's robustness extends beyond simple grasping tasks. This task requires both object manipulation and precise placement, reorienting a spoon and inserting it into a dishwasher rack. Now we introduce a double challenge: human perturbation and sensor corruption. Human perturbation is introduced while a camera is blocked. Despite losing half its visual input, the policy successfully adjusts the spoon's orientation and completes the placement task. These demonstrations reveal the key advantage of our policy. Rather than forcing all sensory inputs through a single fusion bottleneck, our framework allows each modality to maintain its specialized expertise, while a learned router determines which representation should dominate based on the current context. Our compositional framework enables plug-and-play modularity. Watch as an RGB-only policy fails to grasp the occluded marker on the left, while the same RGB policy composed with an independently trained tactile policy succeeds on the right. The tactile expert was never trained alongside the RGB policy, yet their combination works seamlessly, demonstrating how new sensing capabilities can be added without retraining existing systems. Our method can encounter failures. For example, if one of the cameras is blocked, relying on a single monocular RGB camera may result in lost distance information, which in turn reduces manipulation precision.